All right, we're continuing with the quiz review 6.2, 6.3. This is the back page. Let's look at number 3. In a certain culture, the rate of growth of bacteria is proportional to the amount present. If there are 1,000 bacteria present initially and the amount doubles in 12 minutes, how long will it take before there will be 1 million bacteria present? So the two variables that we're dealing with is time and bacteria. So T representing time, B representing bacteria. Time is the independent variable. Dependent variable is bacteria. So we know that initially, when time is 0, we have 1,000 bacteria. We know that the amount doubles in 12 minutes. So after 12 minutes, we're going to have 2,000. So then the question is, how long will it be before there's going to be 1 million bacteria present? Okay. We're going to use these ordered pairs to help us find our C value and our K value. And once we have that, we can find our specific growth equation and plug in 1 million to solve for time. Right, so let's see if we can create our differential equation. It says the rate of growth of bacteria is proportional. So rate of growth of bacteria, we know that this is bacteria is represented by B, but this is the rate of growth or rate of change. So this is referring to B prime. So we can say B prime is proportional. So this is in the form of y equals k times x. So B prime is equal to k times the amount present, the amount of bacteria present. So B prime is equal to K times B. So that's our starting differential equation. We want to represent our differential equation in a more specific manner. So B prime, we're going to write it as dB over dt. Let's separate the variables. We want the dependent on the left and an independent on the right. So I'm going to divide both sides by B and move the dt to the right side. So next, once we have the variables separated, we can take the integral of both sides. So the left side is simply natural log of the absolute value of b, and the right side is k times t plus c. So that's what we have. Okay. Once we have that, we want to solve for b, so we want to find a way to get this b out from under this inside this natural log function. So we raise both sides with e as the base. And once we have that, then this cancels out to be just the absolute value of b, and we know that that b is going to, the absolute value will drop away eventually, so we have it drop out. And then e to the kt times e to the c, we're trying to separate this using exponent property. And this represents c, this is a constant, e to the c is a constant, so we can pull that constant in front, so b is equal to c e to the kt. Okay, now we have our general solution. We're going to take, we're going to plug in the order pairs one at a time to solve for our missing variable, missing information. We're missing the C value, we're missing the K value. So let's plug in the first order pair, 0, 1,000. So 1,000 plugs in for B, 0 plugs in for T. So K times 0 is 0, e to the 0 is 1, so our initial amount C is simply 1,000. So B is equal to 1,000 e to the kt. Next, we are going to find our K value. So let's look at the other order pair, 12, 2,000. So plug 2,000 in for B and plug 12 in for time. And we're going to take the step-by-step, try to get this k, try to solve for k, but let's isolate e to the k times 12 first. So I'm going to divide both sides by 1,000. So 2,000 divided by 1,000 is simply 2. 2 is equal to e to the k over 2. Take the natural log of both sides because we want to bring this k times 12 down from its exponent position. So we can bring, so we take the natural log of both sides. K times 12k comes down in front, natural log of v drops out, and next step we can take is simply divide both sides by 12, and we have k. Okay, so we have our k value, we have our c value, now we can create our specific growth function. Last step is to plug in 1 million bacteria to find out how long it's going to take before it reaches that value. So plug 1 million in for B, and we're going to take step by step to solve for T. So divide both sides by 1,000, and you get 1,000 equals e to the ln 2 over 12 times T. We're going to take the natural log of both sides so that we can bring this exponent down in front using a log properties. So once that comes down in front, we have ln of 2 divided by 12 times T is equal to natural log of 1,000. Divide both sides by this fraction to solve for T. So we get 12 over ln of 2 times ln of 1,000 is equal to time. And then we simply plug all this in the calculator, and we see that it's going to take close to 120 minutes before the bacteria grows to 1 million. Okay. All right, let's look at number 4. Newton's law of cooling states that the rate at which the body changes temperature is proportional to the difference between this temperature and that of the surrounding medium. So the formula is the rate at which the body changes temperature, and so that's represented by temperature is represented by y, so I'm going to use dy over dt to represent the change in temperature, is proportional, so y equals kx, to the difference between the temperature and that of the surrounding medium. So temperature is y, and the surrounding medium in this case is given in the problem to be 35 degrees. So room temperature is 35 degrees, or the temperature in the air is 35 degrees. So this is our differential equation. Time is the independent variable. Temperature is the dependent variable. We know that initially the body temperature is going to be 120 degrees. So at time t equals 0 is 120 degrees. After 40 minutes, drops to 60 degrees. So then what's going to be the temperature after 100 minutes? Okay. So we're going to use this information to plug in once we solve for our differential equation. Okay, so first step, we're going to separate the variables. So once we separate the variables, this is in the form of 1 over u, so this is natural log of the absolute value of y minus 35. I'm just skipping the steps for u substitution because the derivative y minus 35 will not produce anything more than just a 1 for its derivative. Okay, is equal to the integral of k dt, so k becomes kt plus c. We want to get to this y minus 35, but it's stuck inside natural log, so we raise both sides with base e. So we have y minus 35 is equal to a to the kt times e to the c. E to the c is a constant. We can pull this in front. So now we have our general solution. Plug in the ordered pair. So 0 plugs in for k, for time. 120 plugs in for y. So 120 is equal to c times 1 plus 35. So c is equal to 85. Okay, so notice that your ordered pair, your y value is not necessarily always going to be the c value, as demonstrated in this case. Here, the c value is 85. So once we have our c value, we plug in, and we can use the other ordered pair to find the k value. So 60, let's plug in 60 in for time, and 60 in for temperature, and 40 in for time. So once we have that, we get 60 is equal to 85 e to the 40k plus 35. Okay, step by step, let's get the e. Let's get closer and closer to that we can solve for k. So subtract 35 from both sides, gives us 25. Divide both sides by 85, and then finally we can take the natural log of both sides, so I can bring this 40k down in front, and then divide both sides by 40. So we have our k value. Once we have our k value, we can plug in and we can identify our specific equation. Once we have our specific equation, then we can solve for the temperature after 100 minutes. So plug 100 in for time, for t, and the rest goes in your calculator. Solve for y, and we get y is equal to 38.988 degrees.